I am Jinrong Yang. Today, I'd like to share with our work, namely, real-time object detection for streaming perception. In this work, we propose Stream YOLO to solve the problem of time delay in autonomous driving. As we all know, autonomous driving requires the model to perceive the environment and react within a low latency for safety. Let me give a detailed example. Given a car driving 100 kilometers per second, if nothing is done to make up for the time delay, it will produce an estimate error of at least 0.9 meters. The estimate error may trigger irretrievable results. This issue is often concerned in engineering, but there is little related work in academic research. To this end, an excellent work towards streaming perception formulates the issue as streaming perception and proposes streaming average precision to integrate latency and accuracy into a single metric for real-time online perception. To ease the problem of streaming perception, recent works propose a series of post-processing methods with a suitable scale input to search a better trade-off between accuracy and latency, such as dynamic scheduling and Kalman filter-based prediction, and manually searching for input dimensions. Instead of searching for a trade-off between accuracy and latency, we aim at designing an end-to-end detector to directly perceive the future. To this end, we conduct empirical analysis. As shown in the top right figure, non-real-time detector may miss many image frames and produce long-time shifted results. For real-time detectors, it avoids the shifting problem with a fixed pattern of matching the next frame to the current prediction. In the case of low-resolution input, the performance gaps are small for two detectors as they are all running in a real-time manner. However, with the resolution increasing, the performance drop of mask RCNN gets larger as it runs slower. For YOLOX, its inference speed maintains real-time so that the gap is not correspondingly widened. It indicates that real-time detector equips two properties. 1. It maintains the maximum performance lower limit since it doesn't miss any observation. 2. Its fixed matching pattern allows to conduct deterministic supervision. Therefore, our key idea is to employ real-time detector for predicting future. In addition, we further put forward three other requirements. 1. Capable of predicting the future. 2. Keeping real-time inference speed. 3. Maintaining the same performance as offline setting at rest. We hope our approach is simple, strong, and high speed. We first introduced two initial designs. One is the easiest way. It directly uses the ground truth of the next frame to train detector. It only achieves one SAP gain. While it can improve performance and is extremely simple, we think it is overfitting the dataset and not reach the accuracy requirement. The second way is to fuse two adjacent frames and predict next one frame. The scheme shows significant performance improvement by 3 SAP. The result is reasonable since forecasting future need to compare at least 2 frames of information. Okay, along the second line, we publish a strong baseline by ablating its prediction task, fusion feature, and fusion operator. This far, the strong baseline agrees with only the first requirements. It failed to perceive stasis like offline setting, still showing 1.9 SAP gap. We suspect that the concatenation operation may lose some static information like classification. Therefore, we propose a dual flow perception module, namely DFP, which consists of dynamic and static flow. Dynamic flow is the concatenation operation, while static flow is a residual connection. By using DFP module, the performance of static state is the same as offline setting. Moreover, the accuracy of 1x speed and 2x speed is further improved by 1.3 and 1.6 SAP, respectively. We infer that the static flow takes on more roles at rest, and adds classification information in the dynamic case. Next, we propose trend-aware loss to focus more on moving faster objects. To this end, we first define a MIOU for measuring the moving speed. We first calculate the intersection over union matrix on current and last frame, then the object of last frame with max IOU is acted as the identical object of current frame. The larger the MIOU, the faster the movement. We use the reciprocal of MIOU as reweight factor for regression loss. A controlling factor tau and v to weaken the contribution of new objects so as not to interfere with training. It further boosts the performance at any speed setting. Finally, the double frame inference scheme will bring about near double inference time, which doesn't agree with real-time inference speed. Thus, we introduce a feature buffer to cache a FPN feature for inference in next frame. The scheme helps save extra latency. We carry out experiments on several Argovers HD dataset. Our method improves offline detector significant performance with all version models at 1x and 2x speed. Compared with Kalman filter forecasting manner, our method shows better performance and faster speed. Perform better at faster speeds. Moreover, our method achieves the SOTA performance, which outperforming other advanced methods by a larger margin. We further visualize the predictions. Our method alleviates the mismatch and fits accurately between the predicting boxes and moving objects. It further confirms the effectiveness of our method. Thanks for your listening. If you have questions, please leave your message or contact me directly. Our code and pre-trained models are released. You can scan the QR code to get them.